presentation of his thesis, which is called Development of the Electrolyte CPA Equation of State. And we will welcome Hannes, and we also welcome the examiners, the Associate Professor Philip Prosper, who is the internal examiner and the chairman of the committee. And from BP Chemicals in Sunbury, we have Dr. Nikos Diamantonis, and from Hafnium Labs, just nearby, we have Dr. Björn Maibo Monsen. The format is as follows: that Hannes will have a presentation of his work for the next 45 minutes. We will take a very short break, 2 minutes or so, after which the examiners will ask some questions about the thesis and about the presentation. And I hope that they've decided in order amongst themselves. If not, they should probably think about that in the next few minutes. If anybody else has a question after they're finished, they're welcome to ask, but they need to inform me during the presentation. There's no specific time limits on the question, but the whole defense must be finished by, at the latest, 4 o'clock. And I think that's all we have for now. And please go ahead, Hannes.
Thank you. Yeah, everybody, welcome to my PhD defense, where I'll present my work. And the thesis is actually named Extension of the Electrolyte CPA Equation of State, while the project is named Development. And there's a slight difference that we don't want to walk into any more than that. A quick presentation outline of what I want to talk about is have a quick introduction, and then I will talk about the model that I've been working with. And then there are 2 main development parts of the project. One about simultaneous description of activity coefficients and salt solubility, and one part about developing an ion-specific polarization of the model. And we will finish with some conclusions and remarks about potential future works. Now, electrolytes are important in a lot of aspects of chemical industry and other parts. Usually when I'm asked at a family party, what do you do? I always tend to the simplest possible solution to talk about what I'm doing and say, you know, when we salt the roads in the winter, we have a freezing point depression of the ice, and that therefore we don't have slippery roads. So that's a very simple application of electrolytes. They're also present in the batteries. There's also places where we don't want them, but we have them, like in water coming out of the sea, for instance. And we see a lot of scaling in pipes, which we don't want, but we do. And in many industrial applications, for instance, in this H2S plant schematic, you can see there is electrolytes as part of that, and many others. As I said, we want to be able to model these electrolyte solutions, for instance, in order to predict when these scales happen and try to prevent them, instead of having to do experimental work in order to determine all of that. When we model electrolytes, we often see they have a different, they work in slightly different ways than many other types of compounds. Most compounds adhere to van der Waals forces, all compounds do, but that is the driving force of the interactions between them. And while electrolytes also have Coulombic forces on them, and the potential function here, you can see that the van der Waals, they are proportional to the inverse of the distance to the power of 6, while the Coulombic forces are only to the power of 1. That, in this short schematic where I just made the function 40 over r to the 6 and 40 over r, you see that the distance where you have significant values are much, much longer for these type of forces. Now, when modeling electrolytes, this is typically and traditionally in industry been done by using activity coefficient models, such as the PITSR, the electrolyte in RTL, or the extended Uniquark model, or similar models. However, those kind of models do only apply to liquid phases, and that means that when we have vapor phases, we need to use a gamma phi approach where the vapor phase is also accounted for by an equation of state or assumed as an ideal gas or stuff like that. Also, activity coefficient models are by nature low pressure models. there have been different ways to try and circumvent this and use them at higher pressures. But in the true nature of the models, they are low-pressure models. In more recent decades, you can say it's been a while now, there's been a lot of work on electrolyte equation of states from different research groups trying to do different models. However, none have developed a model to an extent where they have seen the same commercial success as we have seen for instance, the PITA model, which is in many cases the go-to model. This has to do, amongst other things, by the fact that many developments have been stopped short of a wide enough range where they are universally applicable. In many cases, they have only been used and tested at low temperatures, like for instance 25 degrees is the only temperature. And in other cases, the number of salts and ions that have been considered has simply just not been wide enough. So this is an ongoing project for many groups developing these type of models. We know from a 2010 survey done by the Working Party of Thermodynamics and Transport Properties in the EFCE that industry sees a need for these type of models, and that that electrolyte modeling is not on the same level as other thermodynamic models, and that is some of the driving force for developing the electrolyte, our CPA equation of state. So my project, or the electrolyte CPA project, is a part of the CPA project, which primary focus is to develop or maintain the entire CPA equation of state. It's primarily and lately been funded by BP, Equinor, and Petrobras in the latest, and previously also other companies. The overall goal of this electrolyte CPA is to develop an extension to the CPA equation of state such that we can use the existing CPA for all non-electrolyte related purposes, and it reduces to that, so that while we have electrolytes, we still use existing CPA parameters for other compounds in the mixture. My project has been built directly on top of a PhD project by Bjørn Mogensen Mogensen, who is also here as an examiner, and that work had three main parts. First of all, there was an investigation of the two main electrostatic models, concluding that they perform similarly, and the second part was to develop a model for the dielectric constant for associating mixtures, and finally a formulation of this eCPA equation of state was proposed, which is the basis of my work. Now, the aim of my project has been to test the limits of that existing model framework and to develop an ion-specific parameterization for the model, as that was not part of previous work. As I said in the agenda, there are two main parts of the work, which have both been published in separate papers. And just when we talk about the project as a whole, I just want to mention that the project was funded by the DTU and the CPA consortium, specifically BP, which I would like to offer my gratitude for. Now, the electrolyte CPA equation of state consists of many things. I bought this very nice slide from Bjørn's original presentation because it's good. And the CPA is essentially these two parts. The SRK, the cubic equation of state, along with the association, which works very well for associating liquids such as water. However, when we need to extend this to electrolyte, we need more than that. We also need a long-range electrostatic contribution for the interaction between ions. In this case, we use the Debye-Hückel equation of state, or the Debye-Hückel equation. And then we also add a Bohren term, which accounts for ion solvation, and has one of the primary objectives are to keep ions in the polar phase. So we, for instance, don't model ions in a vapor phase, which does not make much sense. I don't want to go through all the equations for this, but I just want to show quickly that The cubic equation, which was part of it, was a fairly simple equation. When we then add association to get the CPA, it becomes more complex. Here I've highlighted the 5 adjustable parameters in the CPA equation state. When we then add the two terms for the electrolyte part, we add an additional 3 user inputs. There's a size parameter in the Debye-Hückel part. There's a size parameter, known as the Born radius here in the Born part, and then there is the dielectric constant, which are present in both of these terms. In total, that gives us 8 pure component user inputs to the model. For the mixing of salts and ions in solvent, we use a mixing rule, the homogeneous analytic mixing rule, with the excess Gibbs energy part model using an NRTL model. We then simplify that by setting the non-randomness parameters to 0, simplifying it to this, which has a single interaction parameter between the solvent and the electrolytes. However, for using this in an extended temperature range, it is found that we need to have a temperature dependency, a quadratic temperature dependency, which has effectively 3 input parameters, a reference state which is at 25 degrees C, and 2 additional parameters for this. If we then summarize all the parameters, we can say that we have these 8 pure component inputs, and we have 3 interaction inputs. Now this is the model as it is frameworked, and then based on that we can go into the first part of the work, which was about this simultaneous description of activity coefficients and solubility. Now in the original parameterization of the work, data for osmotic coefficients and activity coefficients was used to adjust the parameters of the model. In this work we wanted to see if we also matched or used solubility data in this optimization, how that would impact the 2 other properties. And we've done that on a small system of 7 ions and a total of 12 salts. And while we want to compare our new parameters to the parameters of the original parameterization, we also in this study compared it to the activity coefficient model, the extended unicrack, in order to see the performance against a well-documented model. Now in this parameterization, we choose a lot of assumptions and choices in order to simplify the number of parameters. First of all, we assume that no association happened for any salts or ions. We also assume 0 value for the energy parameter of the SRK part, under the assumption that the energy would be modeled by the interaction parameter instead. We then relate the co-volume of this SRK to the size parameter of the Debye-Hückel, and we assume this to be hot sphere diameter literature values. As I stated, Bjørn developed a model for this dielectric constant, which is applied here to account for this for associating liquids. And in the original parameterization of the work, the Born radius is adjusted to enthalpy of hydration. However, as we do not change any of the other size values compared to that work, we decided to just fix this value to the work of the original parameterization, because the impact would be very small and negligible if we choose to update this to enthalpy of hydration as well. Now, while this framework is ionic specific at nature, which means that each of these should be specified for each ion, the interaction parameters are chosen to be modeled as salt specific. That means that for sodium chloride, for instance, the interaction parameter is only modeled for the entire salt using data for this one salt. And we do that for all of the salts in the study. In the case of a mixture where there are 2 salts, there is a need for having a common ion in place, because then we can choose to use a relation where we fix the value of this and then back calculate what would the other two non-common ions of the solution be of a value, and that means that we can get a mathematically equivalent value for the parameters, even though they are not contributing to both of the ions. So, as I stated, that means that we account for all of the pure component parameters here, and the only thing that we want to adjust are the interaction parameters here between water and each salt. Now, in the original work, this was done to osmotic coefficient and activity coefficient up to ionic strength of 6. While in this work, as I stated, we want to add solubility data. However, if we use solubility data, we are at the solubility limit per definition. And therefore, it does not make any sense to limit the other types of properties that we use to an ionic strength of 6 if the solubility limit is higher than that. And therefore, we use data in the entire solubility range. When we model solubility, we need to account for the solids and so on. And that is done through standard state properties such as the Gibbs energy and enthalpy of formation and the heat capacity. These values should be defined and known. However, while for salts that precipitate without hydrates, these values are known, and for instance in this database, for salts precipitating in hydrated form, these type of values are not readily available. Therefore, it is chosen to adjust these, treat them as adjustable, and for every salt that precipitate in a hydrated form, adjust these to the data, the solubility data that we have. And we use initial guesses fitted to a different model as our initial guess. Now, if, for instance, for the potassium salts, there is no hydrated salts precipitating, that means that the parameter estimation is fairly simple, because we can just state that the standard state properties of the solids are fixed, and we can just fit the model parameters to the data. However, in case of magnesium salts, almost all precipitating salts are hydrated in some form, which means that we have both the model parameters and the standard state properties that we want to adjust. Therefore, I have used this procedure where we first update the standard state properties, then the model parameters, and then we iterate that until we have some sort of convergence. When we do that, if we move on to some results of that, we can see here sodium chloride and potassium nitrate. For sodium chloride, we see that both, let's just, first of all, the solid lines are the new parameters of my work. The dashed line are the original parameters, and the red lines are the comparison to the extended unit crack. We see that we, with our new parameters, match the solubility in the entire range as was the goal. We also see that the original parameters match fairly well in the lower temperature range. However, there is a deviation at the upper range, at the high temperature range. This is specifically evident here for potassium nitrate. However, nitrates also have extremely high solubilities compared to other salts, so it's fairly expected. A salt like potassium bromide, we see the same. And we also see that in order for us to move from this to have an accurate description of this, we have a very high penalty in deviation of the activity coefficient as seen between this number and this number is almost doubled. In the brackets, we have values only up to 110 degrees, because that is what we compare with the extended unit crack. And we see that this big difference is only evident at the high temperature, because the low temperature values are much closer to each other. As I stated, the magnesium salts precipitate in hydrated forms, as we see here. And it has much more complex path than the other salts. We also see that both parameters of this work and the original work fairly accurately describe these paths whenever we adjust the standard state properties to the original parameters as well. If we then look at some of the properties that we wanted to see how they were impacted by this, we have here the activity coefficient of sodium chloride. And we see that at 25 degrees C, the performance of the two parameter sets are almost identical, whereas at the higher temperature, there's a difference. This corresponds well with the fact that in order for us to have better accuracy of the solubility at higher temperatures, the model parameters are drawn towards having accurate there, and therefore we have less accuracy on different things. And that's just the same. We also see something like sodium nitrate, where we see that all reasonable prediction or correlation of the data are lost at higher temperatures because we have so much emphasis of getting the solubility accurate. Also, one way I've looked at the deviations are as a function of temperature. This is for sodium chloride, the osmotic coefficient and the activity coefficient. And here the dashed lines are limited to the 6 molal data limit that we see. At high temperatures for the osmotic coefficient, that it's only the high molality data that are very inaccurate, while at lower molalities we actually have a very acceptable deviation. A final study that was done in this part of the work was to see what if we say, okay, we have a big penalty in other properties if we want to match this. What if we then, for an engineering purpose, say we can just adjust this standard state properties as well? And if we do that for this potassium chloride, we see the green one is if we adjusted that standard state property, we see we get much closer to the original parameters, and we don't get this very large penalty at the high temperatures that we otherwise got. We then, at the final stages of this work, applied it to mixed salt osmotic coefficients with a very similar performance between the two parameterizations, and this ternary salt system where we actually does see some difference in deviation. We also applied it to mixed salt solubility, and we see very similar performance at all the low temperatures, except for this at 200 degrees C. And this is what is expected because it was at high temperatures that the original parameters started to deviate in solubility, whereas the parameters of my work forced to fit it within that framework. So therefore this is accurate with the new parameters, while the original parameters are not accurate. This is just similar to that. We see accuracy in the entire range. And then also this fairly complex system. The interesting part about this is that in this we have some complex precipitates that are not found in the pure component, the pure salt solubilities, and in that case we have adjusted these the standard state properties to these manually in order to fit best possible this, because we have no other way of determining them. And that mainly concludes the work of the first part, and a few overall conclusion is that on average we are able to model both the solubility and the other properties without losing significant accuracy, especially. We also saw that in cases where we have salts that are not hydrated, and therefore the standard state properties were fixed, we have we see that in order to match that, we get big deviations at high temperature and high molalities for the other properties. Overall, and we see very similar performance for the investigated properties between the eCPA and the extended UNIQUAC, and we saw that we satisfyingly could predict both mixed osmotic coefficient and mixed salt solubility. That was the first part of my work. The second part was about developing an ion-specific approach to the parameterization. As I stated before about the salt-specific work, there was a need for a common ion. because that was the only way we mathematically could calculate ourselves into what, if we fixed it at 0, we can back calculate the 2 other ions and say what should they be to get an equivalent mathematical expression. If we then look at a system where there's no common ion, like for instance sodium chloride and potassium bromide, one could say, well, it's easy. We just say the sodium chloride parameters go into these 2 and the potassium bromide go into these 2. And that might actually give reasonable performance, but it's not consistent and it's not unique, because what if we instead have sodium bromide and potassium chloride? That would be the exact same ions in the solution, but with different model parameters giving potentially different results. And therefore, the only way to circumvent this is to determine ion-specific interaction parameters between the solvent and the ions, meaning that we have a unique one for each ion. And that is the purpose of this part of the project. Now, the overall parameterization with this was done for a system of 9 cations and 7 anions, modeling that to the osmotic and activity coefficient, limited at an ionic strength of 6, and in a fairly wide temperature range. The data used are included for 55 salts, and I would just mention that at the end of the parameterization, a Penelux volume translation has been applied to account for the density. However, it is not something that will be in any more of the presentation. Now, if you do this kind of optimization or this kind of parameterization, you can see that while we have in a salt-specific approach where you have sodium chloride, you just have one salt data for matching one salt. However, whenever we do ion-specific parameters, we see that the parameters for the chloride would interact with the parameters of all the other cations in the system. And therefore, the optimization is much more complex than in the salt-specific approach. One way to do this could be to say we have a reference ion, like the hydrogen. We fix suitable size parameters and set the energy parameters to 0, for instance, and then we model then we optimize the chloride parameters to this salt data, and then we fix that and use another salt to get the sodium parameters, and so forth, until we have determined all of the ions, parameters for all of the ions. However, this leaves a very big region like this one, where everything is predicted based on optimization for different salts. And experience show that this is not a very suitable approach, and that the prediction in this area will not be very good. Therefore, a different simultaneous approach where we use all the data for all the salts and optimize the parameters for all the ions is what is applied in this way. Now, as this parameterization is much more complex and there's a lot more interaction between the parameters for each ion, we also have to evaluate if the same assumptions for the parameters could be used as in the salt-specific approach. And during some trials, it was found that while we still assume that there is no association, we still don't use the temperature dependence of the SRK part, and we still find the co-volume from the ion diameter using the same relation. The ion diameter and the energy parameter of the SRK should now be treated as adjustable parameters. Similar to the original parameterization, we want to adjust the Born radius to the enthalpy of hydration. However, in this case, it is done simultaneously with everything else, with the enthalpy of hydration as one of the inputs, and therefore driving the Born radius to match that, as that is the main contributor to that property, it would be driven towards that. And on top of that, we also still have the interaction parameters and the temperature dependence of that. That means that we have essentially 3 pure component parameters that we adjust, and we have 3 interaction parameters between the solvent, which is water, and each ion. And that is how the optimization, that is the parameters that we want to update in this parameterization. We could just say, okay, we do that. We take all the data for the 55 salts and all the parameters, and then we just optimize and see what happens. However, that is a very complex and interlocked process, and the results would probably not be very suitable. However, in order to get as best as possible of initial guess, we start out by a simpler system of fewer ions and a system that is more easily controlled. When we have that optimized to a point where we are satisfied, we added another ion. We optimized that entire system. Until that was satisfied, we add another ion, and so forth. And then we consequently add a single ion, optimize the system until we have the entire system in our optimization, and we can optimize all the model parameters with all of the data. Now, if we look at the overall result doing this, here's the average. We see that compared to the salt-specific approach in the original parameterization, the parameters increase, the average deviations increase with around 1 percentage point for both the activity coefficient and the osmotic coefficient. However, we also see that for some salts, like for instance sodium sulfate, the deviations are much, much higher using these ion-specific parameters than they were for the salt-specific parameters. In order to account for this issue, it was decided that we added another parameter, an interaction parameter between the ions. Like for instance sodium here and chloride here, we added an interaction parameter in the mixing rule of that, which we then estimate to the same data as we used in the parameterization. However, this can be done for a single salt at a time, and thus be a much simpler optimization. If we look at sodium sulfate, which was the one that I exemplified with having very bad representation, here's the osmotic coefficient of sodium sulfate. In this, the solid lines represent the ion-specific parameters. The dashed line represents the ion-specific parameters with an optimized Kij, an optimized interaction parameter between the ions, and the dashed dot line here represents the salt-specific parameters. And what we see is that adding this interaction parameter greatly increases the accuracy at both low temperature here and at high temperature here, and also makes the deviations for the salt overall much more comparable to the salt-specific deviations as seen here. Also, it lowers the average of every salt, also much closer to the salt-specific parameters. It should be mentioned that these ion-ion interaction parameters were found for 20 of the 55 salts, or ion pairs. This is not because I haven't investigated if these interaction parameters were for the other 35. It's just because for those the optimal value was 0 or extremely close to 0, such that it had no practical impact on the performance. It should also be noted that these interaction parameters are estimated with these ions only in water. And it is not given that the performance would be the same in any other solvent. Now, if we then look at the performance graphically, here for sodium chloride and magnesium chloride, we see that while the deviation overall for sodium chloride between the salt-specific and the ion-specific approach are very similar in average deviation, the trend of the way that they describe the data, the trend of it is different between the two. And then for magnesium chloride, it's interesting to see that the data involved in the optimization are limited here to 2 molality, because that is where we have an ionic strength of 6, which means that all the data to the right of this, in this case, are predicted, or all the modeling of this is a extrapolation, you can say. And what is interesting with the iron-specific approach is that it actually captures this fairly steep increase here at the low temperature. However, it is also seen that having that increase makes it overestimate the increase at higher temperatures, whereas the salt-specific parameters systematically underestimates it. We then applied these parameters to osmotic coefficient of mixtures, and with fairly acceptable average deviations. I have highlighted these two systems because they come from the same paper, the data of them. They effectively include the same ions, but from dissolving of different salts. So the ions in this system are identical to ions in this system. However, and therefore mathematically and modeling wise, the parameters and the model should be identical for these two systems. We, however, does see quite a difference in deviation. And I just wanted to highlight that because this emphasizes the fact that the model has no uniform, does not have uniformly deviations across the molality range. For instance, the magnesium sulfate pure component or single salt and water osmotic coefficient has the highest deviation around the minimum in the osmotic coefficient, and in this case, the data, much of the data in this system that they have here are situated around places where they have some of the same ion compositions as would be for magnesium sulfate single salt there, where they had the highest possible deviation, whereas that's not the case in the other one. So it's about localized deviation based on the amount of salt. Also, we applied this to the osmotic coefficient of a brine with this composition. Obviously, a brine is dominated fairly significantly by the sodium chloride content, and therefore we would expect with good description of sodium chloride that we would have acceptable description also of the brine. And at low temperature we see a very accurate description, whereas at higher temperatures we see a higher deviation, as seen here. And also, we applied this to the solubility, similar to the previous work. And in this case, we just updated we estimated the standard state properties of the solids using the fixed model parameters here for magnesium chloride, giving a very acceptable solubility description in the entire range, and here for magnesium sulfate with the same result. We also applied this to a mixed solvent solubility, and here we have the pure water solubility of sodium chloride and sodium sulfate, whereas the further we go down here, the more methanol we get in the system. And this is the salt that we also discussed had a very where we found a KIJ because the performance was very bad. So whereas the description gets somehow a little bit worse the more methanol we could make, this could also have something to do with this KIJ, but there are the fact that we don't have a systematical prioritization for other solvents could also have a very big impact. In this case, we only estimated an interaction parameter between methanol and the two salts for this single system, whereas the other one is universal parameters. Furthermore, we looked at the vapor-liquid equilibrium here for water methanol with lithium chloride, where we see accurate description of the salt's impact on the VLE. Sorry. Finally, we looked at the liquid-liquid equilibrium. This is water butanol with potassium bromide. And at first glance, you can say this. You can see that we are fairly close to the data on this side. It looks like that, and here we can see that it ends kind of short. So that means that there could be some kind of issue here. If we look further into it, we can look at the alcohol content in the two phases, and we see that the alcohol content in both phases are not super accurately modeled, but it could be considered acceptable in some cases. The main issue is, of course, the salt content in the polar phase, where almost no ions are found in the polar phase. This could indicate a more systematic and fundamental problem with the assumptions of the model, which is also something we can get back to in the conclusion part. So that was more or less what was done in the second part of the work. In conclusion, we can say that the ion-specific parameter set that has been developed perform overall on average similar to the salt-specific parameter set. We also saw that there was a need for these interaction parameters for a few salts in order for that to perform acceptably. And we also found that for a lot of mixtures and applications, it worked. The parameters performed well. However, for LLE and complex mixtures, we saw some difficulty or problems with the model. Overall conclusions of the work is that that both parameter sets that are presented generally perform satisfying in the range, and the fact that we get it to work in both an extended temperature and molality range is quite satisfying. We also see that the salt-specific parameters are much simpler to obtain, seeing that we only need data for a single salt to model or correlate parameters for that single salt, which means that potentially that is much more. It's easier to get accurate for a single salt, and in some applications that could be preferred. If you want to have a model defined for a specific application that you know should not be used for anything else, that could be a preferred type of parameter set. However, in a more generalized sense, where you need a model you can apply more quickly to a diverse set of things, this is not due to the limitations of having a common ion. That is not to be preferred. So in that case, ion-specific parameters are clearly much more preferred. And then we found some limitations of the model, especially at the LLE part, and it could suggest that the model itself should be evaluated to add different parts to it. If we look at potential future work of the CPA, you can say that if we stick within the current framework of the model, there is a need to extend beyond water as a solvent to have a more systematic approach for obtaining parameters within different solvents. In this study, also only strong electrolytes have been addressed, and there's a need to extend this to weak electrolytes. This could be especially important as dissociation is not always fully seen for all of the salts in question, especially in other solvents. And of course, it would be preferred to apply it to even more complex applications. As I stated, the LLE suggests that there could be some fundamental problems with the model, and it should be evaluated how ion-ion association and ion-solvent association could help make the model perform better in those cases and generally. Finally, I would just like to mention that, of course, Georgia's got a big grant to look into electrolytes recently, and that could essentially result in having completely fundamentally different ideas about how to do this and rework the entire structure of everything into a new and exciting future of electrolytes. Yeah, this journey into electrolytes is not from 2014 and forward. It's not always been about academia and stuff, and I would just like to mention that it's also been a personal development, and you learn a lot from working, and you learn a lot from starting a family, and together it is best. Thank you.
Okay, thank you, Hannes. So now we'll take a 4-minute break. So if we can be here at 10 to 2, those of you who would like to be here for the question session. And I think we will start with Dr. Björn Meyer-Bommel. And you can do it any way you like, but I think it might be nice to come up to the front and
Yeah.
so we can have more of a dialogue in an interrogation.
Yeah, I do have to bring my papers,
No.
but only for inspiration. First of all, thank you very much for the presentation. I mean, now I think back 5 years ago when I was standing there, and well, it's a bit of a journey, the PhD. I certainly know that, and I want to say congratulations because you've now really officially joined a small elite crowd of people who have spent more than 4 years of their lives thinking about electrolytes. Is this sound good? All right. So just to begin with, I want to just ask you, what do you think has happened, say, in the past 100 years that were of significance to electrolyte modeling?
Past 100 years. Well, that's a good question. Now, to start with, if you go almost 100 years back, you can know probably more or less exactly 100 years back, the work of the Bayern Hügel was immensely important for all future things that have happened in the field. It is the basis of almost all of the activity coefficient models that are used widely today, and the basis of a lot of the electrolyte equation state that's also in development around the world. So that is, for me, the most important part that has happened. And since that, you can say that the development of the MSA as well is some kind of significance, but as you also showed yourself, there's not really a lot of difference in the performance of the models. So it might not, for many people, be a big step forward. At least some think it is, but for others it might not be. In more recent years, you can say that the development of electrolyte equation state is effectively started no more than, at least at a big extent, no more than 30 years ago, maybe 40. And I don't think anyone yet has come up with a solution to that problem. I don't think what I have done and you have done have been a finished solution to that problem. I don't think any other people have made a solution that really is satisfying and ready to be considered a model that you just rely on in any, for instance, in any process simulation software and stuff like that.
And that's actually something that brings me to my next point, because I think it's also really important, being at a center that has a strong tradition for applied thermodynamics, to figure out, okay, what is then needed for an industrially applicable electrolyte model. You could say, well, what do the activity coefficient models have today that lack in terms of equations of state, or just in general? What do you need really in order to make something industrially relevant?
Well, actually, I don't think it's a lot about science. I think it's about having the confidence of the industrial people that uses your models. If they believe in the product that you're selling or that your development, then if it's 1 or 2% better or worse, that doesn't really matter that much. It's more about trust and belief that the thing that you are doing are consistent, that the performance are consistent. If it has if your parameters have a 2 or 3% deviation, might not be that important if you know that is consistent across the board. So we need consistency, we need applicability to a wide range of systems, and we need let's just end it there for now.
I think also I'm looking a bit also into the technical side of things. So could you describe an ingredient list that Georgios should have ready in 5-6 years or so, in order to really make a success out of this ERC grant?
Ingredient list. That's yeah. Well, I think we need a model or an approach that, of course, works well in a multiple rounds of different solvents. We need a model that can be applied for a lot of ions, and we need to be, in terms of the modeling parts. We also need to be confident that the electrostatic interactions are modeled satisfyingly, and that for instance the debye is enough. Is it enough? Is it not enough? Do we need to add more? As I stated, association between ions and ions of solvent could be a solution that really needs to be looked into, I believe, and potentially the conclusion could also be that we need a completely different framework for this that tends towards the more non-primitive methods that are seen with the non-primitive MSA, for instance. That could be another solution, but it's also a trade-off of simplicity and in terms of the people using your models. In some cases, they want to treat it as a black box. In some cases, they want to treat it as an expert tool, and that also varies a lot how you want to do things. If it's an expert tool, it needs to be accurate enough for people to trust it, and it also needs to be simple enough for people to use it. It doesn't mean that one person in the entire world knows what's going on. But if you develop a black box tool, then basically anything can happen within it as long as people know how to input things in it.
I think there's also one more thing that I think you forgot to mention, and that's the weak electrolytes.
Yeah, of course.
So, well, weak electrolytes are definitely everywhere just because of the carbon dioxide in air. We have it everywhere in water that touches any surface, you could say, causing corrosion, causing, well, in pipelines that could also be precipitation of carbonate salts or similarly. And of course there are mitigation strategies towards this, but an equation of state framework needs to also look into the weak electrolytes.
Of course.
And what do you need in order to describe weak electrolytes then?
There are different approaches for that, but I think personally that some kind of a chemical model that you attach that uses equilibrium constants to account for this would be the right way to go.
Yeah. Now, I think next steps would be to dive a bit more into the thesis and the work.
Yeah.
And what I wanted to ask you, just, I mean, it touches a bit on what was on slide 9.
See, now I made the mistake of not putting numbers on them. Oh, there is.
Yeah. So
this one.
Yes. So your pure component parameters.
Yeah.
There's one parameter here that I do not think is a pure component parameter.
Okay.
What is this?
Yeah, of course, the static permittivity or the dielectric is not pure component because it's essentially a description of the solvent that you are in. That
in principle, you could say that it's something similar to the volume, but for polarity, you could say. So a very polar mixture has a very high static permittivity. A non-polar one has a low one, and it distinguishes basically between phases of different types. So it could be an oil phase where you would have a static permittivity around 2, and then water phases around 80 Also depends on temperature, volume, pressure. So I would definitely take that out, because
that's true.
that is, I mean, it's actually to some extent not entirely wrong in terms of what others have done, because there you take, say, water and you fit the dielectric constant to that of water, and then you use that as the parameter, sort of a parameter for the model. But I think that is what makes electrolyte CPA different from the others, that this is a physical model that uses this. So I just wanted to clarify that.
That's true. That's a misspoken.
But I think it would be really fun to go into, it was slide 40 perhaps, or 23? Yeah, 23. Because we are looking at these osmotic coefficients and activity coefficients of nitrate salts. And potassium sulfate here. So what really could worry someone is that, well, you're not able to model even the trends. Would you agree?
Yeah, absolutely.
Still, you can describe it with a number. And what is that number? Or with two numbers, you could say.
Well, the deviations.
Yeah.
Like here, you mean?
Yeah.
Yeah. I can say a number.
Would you say that those are high or low, or how easy is it to distinguish between the case where it's a good fit of the trend and where it's a bad fit of the trend?
Well, you can not really do that based on numbers. Of course, if you have very high deviations, it's probably not a very good fit of the trend. But you can have. I'm not sure what you mean then, actually.
So I think the important thing here is that you look at the data and you can tell that it's wrong.
Yeah.
You can say, well, something is odd here. So this is basically a known problem from statistics, that you can have many different types of data sets that have the same, say, characteristics, and you could have the same sort of fit through those data points.
That's true.
And how do you think that affects your, say, simultaneous fit, for instance?
How does that affect my sound? Well, essentially what you can say is that for each, the only thing that is important in our optimization as it is, and what I've done is the distance from the modeling to the data point. And not necessarily if the distance between the model and the data point next to it is in the same region.
But could you imagine a way of including such trends in your fit?
Yeah, that's definitely possible. You can use standard deviations and stuff like that too.
Would a standard deviation help?
What's it called? No, I can't remember this. It's called.
It's okay. I just think that, for instance, to recommend something to the future research, these are interesting outliers, or cases where the extended uniquark is significantly better than the electrolyte CPA. It might be a really good place to.
But on this slide specifically, this is all salt-specific parameters, right?
Yeah. But the problem.
And the purpose here was to, especially for the parameters that I work with here, right? That we emphasized a lot on the solubility, which means that we forced the model to have that accurately, and that, of course, also this is the effect of that. But you can also argument that the parameters from your own work is not following the trend very well, even though it's much closer.
No, I'm definitely. I agree. My work is really shit at producing the sodium nitrate as well, and it's a problem that I think it deserves some attention. Why is it that these simpler salts still, even with salt-specific parameters, well, we don't have that many. Perhaps it would help to have more. Yeah. Perhaps it would be somewhere where we could look into association or other effects that can actually be modeled or can be included in the modeling framework. But apparently the current modeling philosophy does not work for nitrate salts. Would you agree?
Yeah, I definitely will. One thing that I actually tried in a small trial that I never went any further with was to put more emphasis of the higher molality data, because we know that it all starts at 1, and that's no matter what we do. So we know that even though we have a very bad trend, over here it will be fairly accurate, almost no matter what we do, right? Compared to over here. So that was one thing I tried. But also, yeah, no.
Oh, I definitely. Just one comment. Why is it accurate at around 1?
Yeah, because we don't have any salt. That's well, the activity coefficient is by nature 1 when there's no salt. I don't know what you mean.
Well, still, I mean, you could have something that goes like this from 1. I mean, we can always agree that we will be accurate when we are at 1. And then it could go like this, it could go like this, but it goes like this. Why is that?
Well,
so no matter what parameters you put in here, it goes like this.
Well, for the osmotic coefficient, for instance, we know that when we add something, almost no matter what it is, the osmotic coefficient of a water solution will decrease. Because, well,
I'm fishing for something.
Yeah, exactly.
I think the thing is that this is a very characteristic slope of electrolyte modeling, and that's a Debye-Hückel slope at infinite dilution, which is one of the most beautiful predictions, actually, of physical chemistry, in my opinion, over the past 100 years. So it's important because that applies not just in water, it also applies in methanol, it applies in other places with different types of salts, but with some cases where you end up in some odd situations. But still, I think it's important.
Yeah.
So next, I want to ask to a table actually in the thesis. Could we bring that? It's page 61.
This one.
Yeah, if we could just enhance that a bit, zoom a bit in, because I think people in the back are going to have real trouble seeing that.
Where is that there?
So, first of all, what are these?
The enthalpy of hydration.
Yeah. What would you say that it is?
It's it's a measure of energy needed to hydrate. It's so far away. It's been a year since I worked with this, and this is even further away. It's an energy that we need. It's the difference in energy between a non-hydrated and the hydrated. So,
I think
I don't know how to explain.
The thing is, it's about taking something, say an ion, from the ideal gas or a gas state, and then putting it in water. So it's a difference in energies, and we see that the energies are huge. So, for instance, enthalpy of vaporization of water is around 40 kilojoule per mole, and here we're talking about almost 1,000 in that order of magnitude. So what I'm just gonna ask you is, 1% of that number, is that still a small number?
Well, 1% of a huge number is potentially a huge number. That depends. Yeah, but
so it's just you mentioned that it's the deviations are very low because measured in percent they are.
yeah,
But if you actually look into, say, what are the deviations in absolute kilojoules per mole, so the first one, sodium chloride here, that's about 5.5 kilojoule.
Yeah.
It's actually significant. You could say one calorie, kilocal is enough to heat water 1 degree, right?
Yeah.
So there is something here where we have trouble describing these very huge energies that we see with ions or with the electrolytes, and it's just something that makes it intrinsically hard. That's so be careful when using percent, because energies are measured in absolute. And
I think the main purpose of this table was also just to show that the assumption that we could choose not to alter the bond radius from the original parameters is valid, and that the difference is not significant. Then that comes back to your point about the numbers being huge, but
it's not significant in percent, but it might be significant in energy, and energy is what in the end is going to boil water off your tank or similar. So it's very important that you pay attention to small energy changes, and just one of the intrinsic problems with dealing with such systems. So then we can go to slide 18. Yeah, because I think it's a really important subject, actually. The standard state properties. You also say that, well, there's a problem here, because when we need to model solid phases, we actually need to have the standard state properties, and they're not always available.
exactly.
So how do you get the standard state properties?
Well, if they're not available, or if they are available, we find them in databases, of course, like the NIST database, where we have taken all of the standard state properties that we have chosen to fix and not estimate. Then the decision comes back. Well, if we go back to the decision was that at that time that for some of these hydrated salts there are actually data, or there are properties in databases. However, there was very few of them compared to the number that we needed, and the decision was then that if we do it from some hydrated salts, it's an easier distinction to say all the non-hydrated salts or the anhydrated salts are fixed, because we know we have those, and all the hydrates we estimate. But if you talk about how they are determined experimentally, I don't know.
Well, but it's at least something where you could say, well, we can go and measure a solubility, and if we have a good enough model, then we can probably come up with the standard state property. Now, actually, that database that you're referring to, the one from Wagman et al. in NIST, how old is this?
It's fairly old. I can't remember. I think it's 81 or something like that.
Yeah. I think it's 82, 81 or something. And it's to some extent strange that no newer publications are available. So did you look into whether there would be other databases or data sources?
I did some search about it, but not a lot came up about that. So it was quite quickly moved on from that, I will say. But I did do a little search on it, but I didn't find much, so I moved on.
There's another thing that's actually interesting and going to be interesting for the future work, and that's where do you else use the standard state properties? Well, that's for instance in the weak electrolytes and the equilibrium constants. So if you do not have these standard state properties or the equilibrium constants, it's going to be a very hard job doing any sort of predictive modeling on the system.
Exactly.
So probably that's an important place to look into.
Yeah, you could say that it could be a whole project in itself to measure these kind of properties and document them.
Oh yeah, I mean the equipment that you use to measure them accurately at high temperatures and pressures, it's quite complicated. There are some labs that do it, but definitely complicated. I think I'm gonna go to one small thing, and that's about the simultaneous fit that you were doing. So you mentioned that you were doing 55 different salts with 14,000 data points or similar.
Yeah.
And your main problem was that, well, it would take a very long time for the MATLAB algorithm to come up with a result, which of course would render you quite, say, a bit unproductive.
Yeah, I had days where I just waited and done other things, but
Yeah.
I was just waiting on the estimation to finish, and then you had to look at other things while doing that. But
could you have solved it by buying a bigger computer?
You can always make it faster, and you can always, if you have a better computer, it will make it faster. Yeah, but it wouldn't. That depends on your definition of a bigger computer. If we have programmed this to work in the DTU supercomputer and stuff like that, then it'd probably be much faster. But I think that is also dedicated to other things. If you buy just a regular, better computer, it would probably be so much faster, but it wouldn't just be instantaneously. If that makes sense.
Yeah, I'm also thinking in terms of, was it able to run in parallel or not, for instance?
Yeah, that's another part if you use all the cores of your CPU, but I'm no expert in that, and so it's not something I really looked into because that's not where my competences are.
No. All right. So I think that more or less concludes it. I think I want to just ask, so if you could say like 3 topics that Georgios should study next, what would you say that these should be?
What should they be? Well, I think there is a need to evaluate which type of extensions to the already existing model would help or would solve the issue that we, for instance, see with the LLE. To see what should we add to this model that is physically relevant in order for it to work to the extent that we want. Then there is the entire field of evaluating if everything that goes on does actually fundamentally work as we expect, and to figure out if the types of equation that we have chosen are actually the right ones. I think that is interesting as well from a more fundamental point of view. But if we assume that we continue with the framework somewhat similar to that which already is, it's also about extending it to different solvents, to weak electrolytes, and make it more widely applicable.
All right. So thank you, Anders, and let me hand the torch.
Thank you, Björn. And we now proceed with Dr. Diamantonis from BP, Hungary, UK.
Hi.
First of all, thanks for the very nice presentation. and for the very good work you've done over the years, because I've been following your work since you started. It's a highly difficult topic, electrolytes, as you discussed with Björn also. So you've done some brilliant work in understanding and building the knowledge and the gaps you identified. And it is also a highly relevant topic for industry for a number of reasons that you mentioned. So, so my first question is, when you started your PhD, did you run kind of a gap analysis for what's needed for this equation to be extended to? Or is it just a kind of based on intuition or prior knowledge that you picked these ion-specific parameters to work on?
I don't think there was a fully fleshed analysis like that. We had, I think we had a discussion also with Sue from BP, and we got a list of things that she was interested in and that BP was interested in, and that was a basis of the start. But also, the first part of this work, I don't think it was supposed to take this long. That as a part of my work, as it actually did. But we ran into some problems. For instance, after 8 or 9 months, we had to start all over because some reviewers on Bjørn's last paper made some changes. So he made some changes, so we needed to, for consistency, go back and change in order for that. So that of course prolonged that part, and that was I think at that point the idea was to have like an analysis of how far we could stretch this in terms of solubility. Also because solubility was not really discussed by many people in equations of states. It's a topic that really was not touched upon, and so, that of course limited the time that was afterwards because we had to start over. And then the ion-specific part of it, I don't think we made like an analysis, but it was clear that these assumptions of common ions and the fact that almost all other developments in the electrolyte equations of state rely on these type of parameters. It was clear that there was a need in order to bring the model to a better place, if you can say that.
So I guess when you start working on an area like this, one thing is that you can identify whether there is a gap in the theory itself, so adding different terms or modifying terms, and the other is to go for the parameterization approach and say, we've got the theory, we know it works with some limitations and strengths, but I don't trust the way that we have been parameterizing, or I'm going to try something different. So I guess both of these approaches have like pros and cons. Did you ever think to go back and look at the theory and say, there is probably a different term that I could use or modify and avoid doing something different in the parameterization part?
Not within the work that I've been at the time when I did the work. No, I think the decision was that we wanted to see how does this work, how well does it work, and then evaluate based on that.
So if you had to, let's say, go back and say, let me just now look at the theory. Do you identify anything that could be done better? Or let's say, if you had to work on the theory, have you identified any part that could be modified, or maybe any different term there?
Well, I'm not sure. Well, if we go back and say what we look at, of course, as I also mentioned in the presentation, using the association between ions and ions and ions and solvents could be relevant and could have been implemented at some point if that was chosen, if that's what you mean. I don't think that the two core terms of the electrolyte equation of state at any point was up for debate in that, because, well, I inherited a framework that at that time was fairly new, and not while Björn did a lot, it was not. There was not spent a lot of time testing in different manners, and that was the initial approach, that we needed to test this more before we made any conclusions.
Okay. And then when you say that you would look at the association term, how did you imagine that piece of work? Like, do you see any, for example, overlap between what the association term studies as interactions and what the electrostatic terms do? Do you see that maybe by using that technique, you may end up with overfitting or parameters being correlated?
That's definitely a possibility. Whenever you add more complexity and more parameters, you can, especially when, well, all of this is based on, all of these terms and models are based on some sort of understanding of physicality, but at the end of the day, they also have an aspect of practicality, and they also have, and whenever we fit models, parameters in a model, we move further away from the true physical world, you can say, because it would be the best possible solution was that you made a model that described the world perfectly, and then you could have known property inputs that then made the model accurately predict something. That would be the very best case scenario, right? But that's not really a possibility. So it goes somewhere in between having a physicality to the model and having a pragmatic approach to it, and saying that well, you can correlate yourself out of anything if you have the right equations, right? So it comes somewhere in between there, right?
Yeah, I agree. I mean, if you with a lot of parameters, then you make an unphysical model. So was there any point in your when you were working on the parameterization part of your work that you studied which parameter is more sensitive, or let's say to which parameter the model is more sensitive, and then say you could identify whether it is overfitted in some cases or whether the data are not enough to fit those parameters?
Well, I didn't do a fully fast correlation analysis. No, I didn't do that. But for instance, the temperature dependence of the SRK energy parameter, the C parameter, I quickly found out that it didn't make any sense to use that as well as the temperature dependence of the interaction parameter, due to the fact that they were highly correlated, and that was very, very evident in any trials that I did. So I quickly just rolled that out.
Okay. And then did you do that analysis for like some of the parameters you said, not all of them? So when you moved into mixtures, is there anything that you see there happening in terms of parameters? Because in some, when you were fitting the ion-ion binary parameters, you said that for some of the pairs, you said I can use a zero parameter because the value I got is not significant enough. So
when I
I'm
say
guessing
that,
there may be something about sensitivity there, or
no, when I said that, I meant that the values were like 0.000 something. It's a very small numbers. It's not like I said 0.01 is insignificant, but it's very, very small numbers.
So it was giving the same result essentially.
Yeah, basically it didn't change anything. There's also some of the interaction parameters that are listed for some of the solves. They have very little impact on the performance, but they still were at a value that was significant enough to report. The number of solves that were significantly improved due to these ion-ion interactions were not 20, even though there were 20 of them. It was more like 5 to 7. I can't remember the exact number off of my head, but
is it because not all the combinations of anion and cation were relevant to your work, or is there another reason why those pairs didn't really matter?
Well, there's also one of the issues, of course, is that the number of data for each salt is not identical. And now I have to remember back what I did. I think I weighted the data so that no matter how much data was for salt, it contributed equally to the estimation. I think that's what I did, because otherwise sodium chloride would just dominate the entire field, because there's so much more data for that than everything else. But
I was going to ask about that because, as you said, sodium chloride is abundant in measurements, but probably you don't have the same measurements for like strontium sulfate or barium sulfate.
no, exactly. There's much less data, right? And that of course has an impact on how that's done.
So speaking of ion interactions and the parameterization of it, do you see any difference between the way monovalent ions and bivalent ions work in the model? So, and the way I'm asking that is, the reason why I'm asking is that in your slide 46, there is some difference in the, so if you see these two pairs, they have different errors, and I was thinking one is probably bivalent, the other is monovalent. Is that...
Well, the pair that I discussed here, or what do you mean?
Yeah. So you've got, for example, you've got sodium, and you've also got magnesium.
Yeah.
So one is monovalent, the other is bivalent. Could that be the reason why you see that difference?
This difference, I believe, is very much due to, I don't think I have the figure, but I can draw what I mean.
Yeah.
Now, if we look at the osmotic coefficient of the single salt magnesium sulfate, it has a very acceptable deviations, but we also see that the highest deviation and where the model performs the worst are here, in this gap here. And then if I look into the data for these two systems, the system with the higher deviation has roughly the same composition of magnesium and sulfate as this area right here.
Okay.
While in the other system, the combination is at another point. I can't remember if it's higher or lower, but that's what I believe is. It's just due to the localized the deviation as a function of the molality, and that in this specific case you just find data very much situated at the worst possible area where the model performance is worst, and the other one is at a much better place.
So is this deviation that you see like the kind of crossover of the curve with the data? Like here is under predicting, whereas here is over predicting.
I don't think that is consistent.
No, it's not consistent.
It's not consistent. We do see that when we increase temperature, I think consistently we have under prediction of the minimum, the higher the temperature, but at the lower temperature, it's very much not a consistent thing.
Could this be because of availability of points at lower temperatures, which, let's say, force the model to be better at it rather than at higher temperatures?
Yeah, of course.
Or is there any?
Of course, we have much more data at low temperatures than we do at high temperatures. That's true.
So did you take that into account when you were weighting the data for your fitting? Or is it something you would do at some point?
No, I have to think, right? I think... how did I do that? Well, the thing is that the way that the temperature dependence is constructed, we have that the reference here is at 25 degrees. It means that this value will be the same no matter these two parameters at 25 degrees. Which means that obviously we have a single parameter that's fitted for a single temperature, and that is also the temperature where we have the most abundance of data, right? So naturally, the 25 degrees will typically be the best model temperature, whereas the temperature dependence to other parameters, they have to match the entire temperature range of everything else, right? So that's why everything is probably better at 25 degrees.
Yeah, and that leads me to my next question, which is, in the construction of this term, there's a reference part and then there's the temperature dependence. Have you looked at the relative, let's say, relative quantities of the two? Which one contributes more to the total term? Is it the reference or the temperature dependence, or does it change?
Well, that depends on the temperature.
So
I would say,
let's say if you go like 50 degrees higher than the reference, will that term be 10% of the total, or?
I think I can say that. Let's just think about this before I answer.
Because that will probably be an indication of why that happens at
I think
higher temperature.
Well, the reference is probably the main contribution, and the other one is it just moves it a bit. I would say that in most cases this has the most significant contribution. Yeah. We can try to have a look at the actual parameters. That could probably,
because if this is the case, if the reference term has the biggest contribution, then probably transferring reference state parameters from one model to the other may not be the way out of your limitations.
Well, that's not easy to see, right? No. Well, actually, when you look at it now, if I look at it here, the main contribution is actually in the temperature dependence.
Okay.
I would believe if you see, for instance, for this, there's very small value. So, but it depends for magnesium. You see, it's fairly high, and then these one are not as significant, right, as for some of the others. So it varies a bit.
Yeah.
I hope that makes sense. It depends. Well, you can say this temperature dependence is not uniform, right?
Would you expect this behavior of a model, right?
It's not linear, right? So it is. Yeah. It's some kind of a parabola, right?
Okay.
And then, of course, it depends on which part of this parabola that the reference state is. If the reference state is here, it's not as significant as the reference state is here, right?
Okay.
Well,
so
it's difficult to say.
Would you expect like a behavior like this in a model you set up, like your reference term and your temperature dependence may have different behavior for different systems? And is that something that will probably can influence your further parameterization of the model, group it in different groups, like the ones that have equally important terms and others that have like more important term.
What do you mean, that we choose different reference states for different salts? Or?
That, you can group them, like you've got one group which is here, as you said, another group of salts which is there, and then run your parameterization in a different way, so it takes into account this difference.
Yeah, you could probably do that.
Do you think this is the key aspect in your parameterization, or is it the data essentially?
I don't think it's a key aspect, if that's what you mean. But no, I'm not sure I understand your question fully. But
so, what I was thinking is it your reference state which, let's say, causes the differences in the way your model behaves, or is it the data you feed your model for the temperature dependence? Because the next question would be for someone to say, Anders, you've got a good model. I see there are some gaps. Let me know what kind of experiments do you want me to do to help you fit it better. Would you choose reference states or temperature dependencies? Or how would you prioritize these two?
If you, what kind of experimental properties you want? I'm not sure I understand. Of course,
if you want,
we want to have
yeah.
data where we are lacking, right? That's
Okay.
I think that's fairly obvious. We don't really need any more data at low temperatures, 25 degrees.
Okay.
We need a more consistent data set of data at a more uniformly distributed temperature range, right? It's not good if you have a lot of data at 25 degrees and then you have a few data points at 200 degrees. Then you really can't figure out what is the well, if you have a linear temperature dependence, it's easy, just correlate these two. But if you have a non-linear temperature dependence, you can't really use two temperatures to correlate that.
Yeah.
So you need to have like a uniformly distributed, ideally uniformly distributed set of data.
Yeah.
If that makes any sense.
Yeah. Okay. The other thing I was really interested in when I was studying your thesis is around the LLE results that you showed.
Yeah.
So mixed solvents are of very, very significant interest for industrial purposes because you never have like pure water. You may have it with a number of other organics. So I think you said that the most important part in this part of the work is how you model the dissociation of the salt in the organic phase.
I don't think it's the most important, but it's a part of it, right?
So your model without any salt, can it capture the partitioning of organic and aqueous phases?
See, that is it should be, but I don't have the reference to it. Yeah, I think that it definitely could at least to an acceptable degree.
Okay, and then I would have thought that the salt dissociates in a different way in the aqueous phase and in a different way in the organic phase, and then you would probably need different parameters that would be both ion specific and salt specific, because I'm guessing if you're below the solubility limit in your organic phase, you would also have like salt in its neutral phase. Is that right? Or how do you imagine the system? What kind of interactions are you modeling, and which one is missing?
Well, we're modeling this very simple, right? We don't assume any. We assume full dissociation on all mediums, right?
Full dissociation in every phase.
That's the assumption that we're basing this on. That's also what we discussed about weak electrolytes. Yeah. That's an important topic to add to the model because that has a relevance there. So that's how it's modeled. And of course, in this system, for instance, we don't have any systematic approach for the butanol potassium bromide parameters. So those would be estimated directly to this system to best possible work of that. We had a master student in the last parts of my work who worked a lot of LLEs and did a few studies where he manually changed these interaction parameters, showing that potentially for some of these you can actually correlate this type of thing, but it would have a devastating effect over here.
Okay.
And then you can discuss it. In terms of that, I would say if you wanted to look at this from the best possible, it's not good, but the best possible it would be that this is correct, and then you can discuss that this is not. But it would be even worse if this was all over the place, you could say. But none of it is very good.
So in this graph, then there are two trends that your model has, like the opposite trend. So if you see how you correlate the water phase on the left one, and how you correlate the organic phase on the right one, then your model shows totally different trend. Is that something you know why it happens, or you speculate, or is it just parameterization?
I cannot. Well, there might be some physical meaning to it. I can't figure it out. So, but no, I don't have a good speculation in that terms. It could.
Is it a consistent effect you see in all like similar systems?
Well, we only tested this. In my final version of this, we only tested this for 2 LLE systems, and I don't think those 2 are consistent. And in the master student work, he used salt-specific parameters for this LLE, and as I remember it, they were very. There was not a consistent trend, and it was all over the place how they performed and how they behaved. And for some of these, the salt data was like this, and for others it was different, and the prediction of it was also this tends to go up here, and for some of it it's more like the other way around, right? So it was not very consistent how it performed in these types of systems.
Because especially for the right one, I would have thought that, let's say if you have a certain amount of salt in your system, if it increases its presence in the aqueous phase, then it would be depleting the organic phase. So you should have this asymptote or falling trend rather than an increasing one. Yeah. But that's probably one of the limitations you discussed in your thesis. And do you have any ideas on how one would address this? Like, if you were to design the next steps for addressing this limitation, where would you start?
Well, as we also discussed, I think the dissociation of the ions in the polar phase could be an issue, but also account for the association between the ions and the solvent could do a significant difference. I can't say that it will because I didn't do it right, but it's.
Is it like if we go back to kind of basic electrochemistry? If you create this kind of sphere, the hydration sphere around one ion, could that be some perturbation in your association term? Is that what you mean? Because your association term essentially models the hydrogen bonding between your solvent molecules, right? So if you add an ion and then you create a sphere around it, then the interactions between the opposite molecules of the sphere would be different than what your original association term models.
Yeah.
Is that what you were thinking?
I don't know how to answer that actually.
It's just an idea.
But it's definitely one thing that I actually didn't think about that just come to mind now. It's not written anywhere, and it's just something I really think about right now that we're talking about is that when we have other solvents, we also use this dielectric constant modeling that Björn developed for that. But the version of that we use is the one that does not take into account the ion contribution in this. And as I remember, you also developed the version that does that. And I don't think it would solve the problem, but it could be interesting to see how if it made any difference at all to add that to the model.
Okay. And then there was an interesting point around the trade-off you have between the osmotic coefficient and the solubility on the way you fit your model. Is that something that is because of the number of parameters, or do you think it's a theory that can capture either one or the other property? You said that if you fit your solubility well, then your error for the osmotic coefficient increases, right?
If some of the salts, that's definitely the case.
Okay. Is that something that you have thought about, some way of solving it? Is it a parameter issue or is it a theory issue?
That, I believe, well, I think it's primarily a theory issue, right? Because if we trust the properties of the standard states for these salts, and we should, because they are as they are, right?
Okay.
Then we should see that it should be possible, right?
Yeah.
And also there's a direct link between the activity coefficient and the solubility, and the way that we calculate it. There's a direct link between those. But I can't answer what for the nitrate salts, which are definitely ones where you have the highest solubility. You have extremely high solubility.
Yeah.
One issue, of course, could be that you do not have full dissociation at high molarities, which could account for some of it. But for some of the other salts, that might not be the case. And there I don't have a very good explanation on how to solve it.
Okay.
I think there's a clear reason why most electrolyte accretion state studies that are published, they put a limit on this on the ionic strength, because it is an issue across the board, I think, for everybody. And then, of course, when we do this at the solubility limit, we push the boundaries of that
to high ionic strength.
Yeah.
Yeah. So this is what I was thinking. The Schlaikjer model is more like towards the low ionic strengths, right? Whereas your solubility limit may be at higher. Is that what?
Yeah, I think. Well, this goes back to people's how people observe and find the Schlaikjer, right?
Yeah.
A lot of people, when they talk about the Schlaikjer, they talk about one of the simplifications of the model, which truly only applies at very low molarities.
Okay.
Whereas the full version is not having exactly the same limitation, but of course, the higher we push it. There's also a matter, I think Kai once said that when you get so high, at some point you get so many molecules in the solution that the physical properties and the physical interactions overweight the electrostatics, because there is not a lot of distance anymore. So that's also an issue about that.
Yeah. So at conditions of low water content, you would expect the model not to work very well. Is that what you're saying?
Yeah, lower. Well, yeah, it should work better the lower the molarity, right?
Okay. Yeah. Right. And just to link this one to some industrial applications that you showed in I think the first couple of slides.
Yeah.
You talked about barium sulfate scale.
Yeah.
Which is indeed a very important issue in the upstream oil industry.
Yeah, exactly.
And that's a very soluble salt, but then it creates these depositions which are very difficult to take out of the pipeline. But the conditions we see there are probably supersaturated solutions. And if we talk about saturation index or ratio, we're talking about probably higher than 3, 4, up to 30 plus. So we know, if we look at it from the industrial perspective, what we're interested in is guidelines to say, if your water chemistry is within these limits, then you will have definitely some scaling issues. If it's within these limits, you may have or you may not. And then if it is below that limit, you're free to go, because there's nothing really severe happening.
Yeah.
How do you see this model working, especially in the intermediate area of saturation ratios between 3 and 10? something like this. So where it is super saturated, but you don't know if you will have scale or not. I think you mentioned that the model has been validated and fitted up to the solubility limit. But have you done any work on, let's say, checking how it works at higher concentrations?
Not gone beyond the solubility limit like that.
Okay.
But so I don't think that's something that we tested really to see if it could do that.
Okay.
So I don't know what else.
Because I see this as one of the next steps, like take it to higher concentrations.
Yeah.
And understanding whether you can model, let's say, when you will have precipitation and how much. So that's like the thermodynamic limits, which will then be fed into something like a guideline.
But I do think that there is a general there's a general problem when you go to these higher modalities and higher density solutions. I think that is a problem that is seen in many places, and I don't think there's a common solution to that.
Yeah. And so my last question, just a bit broader, even broader than the last. Do you see that you can have like a model which is universal, that you can apply it to a number of challenges, or are you seeing it more like an exercise of tailor-made models for different applications? Let's say if I give you 3 different brines, then you would have to refit for every brine, or is it like more universal parameters which can be used for more than one brines?
Well, in the terms of brines, I would say that depends on what you believe, what you think should be in them, right?
Okay.
If you come fairly close to, if the matter is the composition of these brines and not really the matter of how many ions are in there, I think one model is more than sufficient, and I also think if you have a small variation of ions in your brines, it should be very well possible to.
Okay.
So if I would say that if you wanted to have a model specifically for upstream oil production and production water and stuff like that, I would probably say, well, to hell with having a universal parameter set. Let's look at what you need. Only look at that. Make that as good as possible.
Yeah.
And then I believe that unless you want everything that was in there, the 17 ions, a smaller system works better. If that's what you need, that could be performing much better. I would say you can do that and probably get a model that could work for some of the challenges that you have. But of course, as soon as you go into something that should be used in the wider public, it should be implemented in commercial simulators and stuff. You need to have full applicability. You need to have a much wider scope of what you can do, right? It doesn't.
Yeah.
So it's about. I think both things can work, and I think for a specific challenge, this and many other models can be tailored to fit that specific challenge. Fairly well, in some cases at least.
And I guess one important step there is to assess the predictive capability of the model.
Yeah, exactly.
By splitting your training set, your data set into training and testing. Is that what you've done?
No, I've used all the data.
All the data as training.
I've used all the data. But yeah.
Okay. I think I might have used my time. Thank you for this. Very good work again. Congratulations. And thanks for all the hard work you've done and the user-friendly versions that you also made, like MATLAB and Excel. And
yeah. Thank you.
Thanks.
And as the final opponent is the chairman of the committee,
Thanks a lot, Nicholas. Give me this opportunity to talk to Anders today. So I'm just the person holding you between the champagne and the rest of your life, basically.
Yeah.
It's. I kind of wanted to start out with one word, and that is congratulations, Anders, but not yet, right? Because I'm going to ask you a few questions.
Just spend another half hour.
See, so the bad thing is that they left me 1 hour. Why did they do that? I have questions for 2 hours, right? I don't get it. Okay, anyway. No, but I think let's just start out with a general impression of the thesis. As reading it, I really honestly think it's quite well written. I want to use the word simple, but it's not simple. It's easy to read. It's kind of straightforward. The structure is nice. And I like the fact that you state very clearly what is the aim or the purpose, or maybe the objectives, whatever you want to call that.
Yeah.
Before you do anything, so people kind of see, okay, what are we doing now compared to what we were doing before, and stuff like that. That's a really positive thing. And also, I think the kind of the introduction and conclusion are fairly well written. So congratulations with that.
Thank you.
Okay, enough said about that.
Oh, that was
So let's jump into the pool, basically.
Yeah.
Okay, so let's just start out with a few general questions. Let's just say that I had a company who wanted to continue this work, and they asked me a question: how easy is it to extend this to my system? Well, how easy is it, Anders?
That depends on the system.
Try to explain.
And it depends on your need. If you come to me and say I have this strong electrolyte system that is fully dissociated and everything, I think it would be fairly easy to extend to that because we already have a fairly good framework to just go into that. As soon as you go into say, well, I have this weak electrolyte system, then it's a whole different thing because there is a whole aspect that is not implemented that needs to be implemented.
Yeah.
So that's clearly a step over there. So it depends on the system in that way. It also depends on the purpose. If you want to do a lot of LLE work, you clearly see that doesn't work very well. But if the purpose is to look at solubilities and stuff like that, or look at stuff like that, it's a different question, right? So it depends on the purpose, it depends on the system.
It's giving a realistic estimate, right? Saying, okay, I want to do this for a CO2 system. How long time would it take you to do that? And give me a realistic number, not something like, it's going to take me 2 days to do that.
No, of course it won't take today. Well, I don't know. Well, probably. Well, with no guarantee of it working, I would say I would probably do it within 4 to 6 months. You could probably get
fairly quickly, in my opinion.
Yeah, but well.
So, what does it require for you to get there? Can you say like 3 things which we need to do in order to get there?
For CO2, you need to implement a weak electrolyte step, right?
Mm.
You need to test it, and you need to collect data and parameterize it for the suitable application.
Mm. And the reason why I pick on this so much is because I was just sitting and reflecting on my own life and saying to myself, when did I step into this business? And that was kind of I think to date, more or less 20 years ago today. Maybe it's 19 and a half years ago, but anyway. That was when I had the first experience with extended univac. I remember sitting in an office together with 2 of my classmates, looking at it, and it was just equations after equation after equation. It was, somebody would call it horrible, but some would call it interesting. And I remember 4 or 5 years down the line saying to myself, oh, that's how it is. After 4 or 5 years, right? Then I kind of started to understand what it was about. And I don't think I really did realize before somebody forced my arm on my back, saying to me that now you have to implement a solubility calculation routine. When I realized what it takes in order to do the things and the implementations honestly, I believe implementing the extended Uniquac model, it takes no more than a few weeks. For the quick person, maybe a few days.
Yeah, that's true.
True, yeah. But implementing the flash calculation or the equilibrium routine, which has to calculate that, probably takes the person 3 months, at least, if he's well inspired and has good feedback. I think.
That's probably
That's
true.
what it took me at least.
And you're a smart person, so
I don't know.
probably a little bit longer.
I don't know. But just remember when you're saying to somebody, it's a quick job, right? I agree with you. Having an extension where you take strong electrolytes into account and then continuing that work is probably straight off the shelf in some way based on the framework what you have now.
Yeah.
But then now we have a good experience in the center knowing how to do equilibrium routines, but I can guarantee you it's not an easy task to do.
No.
And then you said another word is that it's really only based on strong electrolytes. Well, I can ask you one other question. Is it? Well, why do you think that I'm in doubt now?
I don't know. And I seriously don't know.
Well, let's say you want to calculate pH. How would you do that? Could you calculate pH in a system like this for the calculation routines that you have?
I never done it, but I don't see any limitations in doing. Yeah.
What would it require to determine the H plus concentration in the solution? How do you do that? Because I did see some of the slides having H plus in the parameter tables, right?
Yeah, we have hydrogen as a compound. We have.
How much of the hydrogen is there? I don't see it in any of the salts.
It comes from the water, of course.
Yeah.
So yeah, you have like the water, hydrogen, hydroxide. Oh no, what's it called? Yeah.
So is water a strong electrolyte?
No.
What would happen if water was a strong electrolyte?
It probably would disappear.
It probably would disappear.
Now you know
Exactly, there would be no water, right? Maybe it's a slight overestimation saying that it's only a strong electrolyte system because water is in no way a strong electrolyte in this case.
Oh, that's true.
And you have a lot of it.
But in terms of all other electrolytes.
Can you then tell me how did you treat that water in the system? There must be some sort of framework saying something about how you treated water completely different from any of the other salts. How did you do that? Be honest with me. Is it because you just define the ions and you have a simple dissociation routine next to it, or how is it exactly? Because I didn't look into the codes at all. I have no idea how the framework is set up.
No, well, water is defined purely as the solvent, basically, right? It's accounted for through its CPA parameters, and it's accounted for through the dilated constant. And other than that, there's nothing discussing the dissociation of water. Other than that, when we talk about hydrogen as an ion, we always talk about it as having, for instance, hydrogen chloride added to the water, and then data measured based on that. So we only discuss the excess, you can say, the thing beyond this natural dissociation of water.
As you see, hydrochloric acid is a very simple component. Let's just say it's a strong electrolyte. It's fully dissociated, so all the H plus ions goes and becomes H plus.
Yeah.
And the contribution from water is non-significant, right?
That's basically the assumption, right?
That's the assumption, and that's also the assumption in the code that you have, basically.
Yeah. I would say so.
Okay, great. So now I understand that. Okay, so let's go into some a few details that I have 1 hour. That's really bad. I can go for the hour. That's so bad. Okay, so let's just start. Could you bring up the thesis, by the way?
Yeah,
let's
sure.
just take a few of the introducing slides. Introducing pages. Let's just start out at page number 10, for example. 11, I think it is.
Just a second.
Okay.
Just talk, I listen.
Okay, I'm gonna talk. This is kind of what I want to pick on now is the philosophy of our thesis writing in some way. What happened there, Anders? Lost connection?
Oh yeah, it's a cable.
Oh, okay.
I just want to
So,
add a mouse to this. That's
or
much
you want to
easier.
add a mouse. That's how it is. It's kind of the philosophy of describing theory and relations and stuff like that. Yeah, keep it like that, and let's just switch to page 11 or something like that. That's page 3, 5, whatever. We have a few pages to go there.
Come on.
I think we're there, yeah, exactly, yeah. So you have this nice equation 3, 2. Maybe you can zoom in so some of the other audience can also see. I can see it because I'm only 29. So it's, you know, this equation here, what is that equation? Just zoom out a bit. I don't expect you, I actually wrote here, how do you derive this equation? But I'm not going to ask you that question. I did that. Don't do it. It says it's something related to the Boltzmann's expression and something about the iron stuff like that, right?
Yeah.
That's how I remember it exactly. Yeah. If you go a bit further down,
Yes.
just here it says this results in the Helmholtz free energy expression for the Debye-Hückel theory given in equation 3.4. Ooh, okay. Sometimes I would really like a bit more explanation of how you got from like one to the other. Simple trick is to say, okay, just refer to a big book somewhere. I can read 300 pages on it. Yeah, I did that a long time ago, and I forgot it halfway through. Maybe I remember some of it, but still, it's. I think there's more than one page coming from that equation to equation 3.4.
Probably.
Probably there is. Okay, so anyway, but that's just a simple trick about thesis writing.
Yeah.
Then there's something about conceptual understanding. Let's go to page number 9 there. It's just a bit up. See, you had a very nice slide, and I was almost picking my arm not to say this, but you see, here it says that there. It says this is the interaction related to polar components, right? That's the forces between two ions, basically.
Yeah.
And there's a link which is very important, which is this power of 2 for the radius. So this means that the farther you get apart, the less the interaction is, but it's related to a power of 2. What does it say about the normal forces, which is not electrostatic? I think you had a slide on this, actually.
Yeah.
It says the inverse of the distance to a power of 6.
Yes.
Do you remember what that radius is typically? How big is the radius? Approximately.
Well,
10
it's
to the
small.
minus. It's small, yeah. How small?
I don't know. I can't remember those kind of numbers. But,
10 to the minus 9 or 10 to the minus 10, something like that. I think that's the order of magnitude, right?
Yeah.
So what happens if you divide by, let's say, 10 to the minus 9 to a power of 2, and you divide it by 10 to the minus 9 to the power of 6? What happens to F in this case? Just assume that's the same order of magnitude.
Well, it will
Is
be
F
much
bigger or smaller in this case?
Well, if you divide it at a very low, it will be bigger. Wait.
Exactly, yeah. Can you see my point? Ten to the minus 9. Really doesn't matter whether it's 9 or 10 or whatever.
But yeah.
To a power of 2 versus 10 to the minus 9 to the power 6.
Yeah.
What happens to F in these two cases?
Well, this
Where
one
is
will.
F bigger?
Well, that depends on what's before this, but this one basically.
Is it?
No, this one. Sorry, this one.
That one, exactly.
Yeah. It will. You have to go beyond 1 before it's reversed, right?
Exactly. Yeah. So what happened in the equation, you think?
Well,
This is supposed to give you a very small F, right? That's the dispersive force.
Yeah.
This is supposed to be the polar interactions, which is supposed to give you a high F. But it's in practice opposite, isn't it?
Yeah. I don't think I ever stated that it was a stronger force.
Oh, you didn't?
I just say that it works on a longer range. But I can't remember everything that I wrote, so I will not.
No, but it really doesn't matter so much. You can see.
But it's still.
My guess is that there is some sort of with the units, right? So the radio is probably given in another unit above, as you say yourself, above 1, right? So it, but it's kind of
There's
it's
no
a
doubt
small
that
detail. The
Yeah.
theory is correct. Everybody knows, but from a basic understanding point of view, there is a missing link. I think the slide gave you much more information. I think actually looking back on your slides, cleared up some of these misconceptions a few places in my mind. So that actually punctured some of my questions. But that's a good thing, actually. No, that's a good thing. So let's just take another basic equation. Page number 16.
Is there not a place where you can just write 16?
So people who have studied
What do you?
extended uniquack for a while would know this answer quite similar. And maybe it's great. I think it's number. No, let's just start out with 16. I think that would maybe. Let me just look at my own pages.
There's only text on that page.
That's a nice question for 16. Okay, let's start out at 16 in the bottom there.
Yeah.
This question for 16 in the bottom, that's kind of a 1 hour question. So no, we will do. Could you do 17 on the right there? This is much better. Just scroll. Can you do 17 in the bottom?
Yeah.
Great, there it is. So for people who've studied extended uniquack for 29 years or 20 years or whatever it is now, this is a very obvious question that I have. You have the equations up here.
Yeah.
Deep success. You have the combinatorial time. Nice. And then you have a few things in here. There is some parameters dug in a few places, some compositions and stuff like that. And then there's this set value there. What is that? Do you know that?
Yeah, I haven't wrote that. The set, the coordination. Yeah. Well, it's
What is it, you think?
the coordination number.
And what is it?
The chance of me saying something stupid. I believe it's something about. What can you say? If you have like a charged. If you have. I'm trying not to say something that I'm not sure. But basically, it's about having if you have some. Your ion will be coordinated to a number of water molecules. For instance.
Neighboring molecules.
Yeah, that will then be 10 neighboring molecules.
Exactly, that's true. Is that always the case? Is all ions always surrounded by 10?
Of course not.
Of course not. So why is it chosen as 10, you think?
Well, I don't know why it's just there. Probably, if you want to have it simple and say that we have a uniform coordination number, I would say that it's an empirical decision.
It's an empirical decision. Exactly. It's kind of a very important thing here. So the next thing I actually wanted to discuss with you is the whole parameterization of what you did.
Yeah.
So you should imagine, I think when I started out with extended uniquack, what I was doing, I was reading all the previous work before that leading up to extended uniquack. Now, I'm not sure exactly about all the historic details, but I know one person who is. But one thing that I did realize was that there was at least 2 or 3 big works on uniquack implementation in relation to electrolytes in some way. And they failed completely. Do you know why they failed?
No.
There was one main reason for it. It's basically the same model, all of them. Smaller corrections here and there. Testing for this and that and that. But there was one main reason for it being successful with the extended uniquack. And that is the choice of how you fit the parameters. and Z is one of them. Z is just one of the simple ones, right?
Yeah, exactly.
It's assumed constant 10. Could have been 11, could have been 9, it could have been a fitting parameter. You could have broken the model completely, making a fitting parameter, whatever. So the whole success, I believe, it's a personal belief. It's not a proof. One of the reasons why it was successful, because somebody, I'm not sure whether it was you, Kai, I think in a late night you probably did that. But there is, somebody chose to make a framework for the whole parameterization in the extended uniquac model, which made it consistent, you could say, which made sure that there's no solutions, that there's no two solutions to the same thing. There is probably sometimes, but the fact is that the parameters actually do give a meaning. And I'm not going to criticize your work and saying one of the reasons why your work could be improved even further is because you didn't follow the same scheme. But there is a definite possibility to change the way of parameter fitting to make it, you could say, consistent. Because let's just take this example. Your way of fitting compared to how the extended uniquac fitting is done. Can you say a few words of similarities and non-similarities? What did you do similar? What did you not do similar?
So that means that I have to remember how
you wrote 2 pages on it in your thesis.
Yeah. Over a year ago.
Over a year ago.
I really can't remember.
Can't remember.
I'm sorry to say.
No,
I really
but
can't remember.
it's you had this very nice figure. Did you have it in the slideshow? I think, where you show the parameter tables and how the parameters were fitted one by one.
Yeah.
I wrote down slide 16.
This one.
That's another thing, right? There's so many nice questions to ask.
Like this one.
Yeah, in here, but there is another one where you start out kind of with the top left square, and then you extend it a bit, and then you extend it a bit. There it is! There it is. So here you started out with a system where you have cations on the top and you have anions on the left.
Yeah.
You decided on this system. What other types of approaches to the parameter fitting did you start out with? Do you know how it's done in the extended uniquac model?
Well, I can't say that I know everything about it.
No, I don't expect you to.
But as I remember, as I said, one possibility was to use a reference ion and then work for that. As I remember, that is what is used in the extended
Exactly, yeah. It's a very, very important point. There's a reference ion, and more or less all the remaining parameters is linked to that. You state in your thesis that I don't remember which page it is right now. I could probably find it in a minute or two. But you state you tried that out actually, but you went away from it. Why did you go away from it?
Well, because the way that I tried it was to say that we have hydrogen chloride and then we fix the hydrogen and model the chloride, and then fix that and then do the sodium, for instance. And that leaves a lot of salts that are predicted. That's not saying that you could do the same as I did, but still have it as a reference ion. I just didn't do that. It's as simple as that. I can't really.
You see, because this type of fitting, now I don't like to criticize because I think it's quite a nice work. But this type of fitting, I think, was done quite similar to. Was it Sander who did this? Who fitted, you could say, with an interaction table where he just let all the parameters float in some way, and that created a. You could say you could probably have fitted the exact same thing with a completely different table, but you got to the same result. But if you have one fixed, you could say, pole in the whole parameter table, which is linked up to a consistent and physical phenomena, in this case it would be the H+ ion related to the definitions in the NIST database. Then you would have kind of what I would call a bootstrap something that would fix all your parameters to a well-defined, consistent setup in some way.
That's true.
There's more than one way to do that. If you read one of the pages in Kite's thesis, there's 2 or 3 different ways to do that. But you have to decide on one of them. And another thing is this table, which puzzles me a bit. Can you see it? Because if I look at a typical interaction table, there is something different with this table compared to many other tables. What is that?
What is different than many other tables?
Interaction tables. This is what I would call. It says even parameterization, right?
Yeah.
It's kind of an interaction parameterization table, isn't it?
Yeah. Well, yes and no.
Yes and no. Why no?
Because we want to. This table is made to exemplify that we optimize the parameters for the ions and the interaction with the ion and water, and not the interaction between the 2 ions.
Why not that? Because if you're thinking about what happens in the soup, I agree that there is an interaction with water.
There's also
Why
an interaction
is there not
between,
an ion-ion interaction?
There is. Of course there is exactly. Physically, but it's not. There's no interaction parameter between them. Of course, the Deborah-Hügel term takes that into account.
See, usually when I look at interaction tables, I have all the ions on the top, cations and anions, and I have all the ions on the vertical axis, all the cations and all the anions. So this means that I have interaction between cation, anion, and anion, and cation, by the way.
Yeah.
So there is, in this parameterization, there is a choice saying that, okay, the only interaction we take into account is something like iron and water, where in the extended unit quark setup, the iron-water interaction is a thing you fix like this. It is done the first 5 minutes when you do it. It's related to something like solubility in water or something similar like that. And then the difficult thing starts afterwards, when you need to determine the interaction between ions. And this is where you do all the complex systems, and you have, well, ternary and quaternary and penternary, whatever, quinary systems, where you start fitting the ion-ion interactions.
But it's absolutely true that the basis for this type of parameterization is only data related to having 2 ions in a system, right? There's no ternary systems used in the optimization.
Mm-hmm. But in principle, you don't have to, right? Let's just say that you would like to have the interaction between, sodium and chloride. You could determine that in a sodium chloride water system. And the same thing goes for more or less all the other systems, right?
Yeah, but that's
binary interactions, not ternary interactions we're talking about. Right?
No, I'm not sure I understand, because I see that I think I see that as how it's done, but it's still I think we talk in different directions. I'm not sure I understand where you want.
Yeah. No, but I think maybe part of the improvement process, what can be done in the future, could probably lie in the parameterization process.
That's
in
true.
In the way that you frame and you hold your parameters. I usually call it the art of parameter fitting, because also, if you've seen, sometimes the parameters go like up in the air. I think you even built in a kind of a conditioning routine which said that the parameters are conditions within a frame,
a limitation,
right?
Yeah, because
do you know why they go like up in all directions?
Well, that's about how optimization routines work, right? Some of it, at least, because
what I have a personal experience. What is your personal experience for something like that? Why do you think you see something like that?
Well, potentially there could be a point with very, very unphysical parameters that has lower deviations, where if you have correlation between 2 parameters, it could be that if one go up, the other one go down, they just continue that way.
That's one obvious thing, that they kind of just do like that, and they go out of the string, both of them, but giving the same intermediate value in some way.
I think that's what I primarily observed in here, because it was never a single parameter that went to extreme values. It was always in a pair where one went the other in one way and the other went the other way.
Yeah.
But there's.
Well, how significant are the parameters? Do you have any idea? So let's just say that you were looking at all the parameters you were fitting, and you looked at them. What is the confidence interval on the parameters? How would you determine that?
Yeah, well, that's somewhat difficult to say, right? But obviously it shouldn't be like a million. It's just like a completely obvious thing.
Yeah.
But, that's what I limited through.
Let's just say you picked on one of the parameters, any of them, or maybe you picked the one which was running away like to a million or whatever. It's not supposed to go there. How would you tell yourself whether this parameter had a significance to the whole fitting process? I can ask in a different way.
Yeah,
is this parameter significant? Do you need it?
You can tell by if you don't have it, if the performance is poor, even worse, of course. That's a very simple way to look at it. If you remove a parameter and say that we fixed this at 0 or we fixed it at some value, and you can still get the same result, it's not significant. But if you do that and the results just fall apart then it's significant, of course.
Yeah. You have this correlation for the delta U value. Can you show that? There's a correlation for delta U somewhere on your slideshow.
Like the temperature correlation?
Yeah. Oh yeah, that's probably the one, yeah.
That's that should be
this one, yeah. What parameters in this equation did you fit?
We fit just doing those three.
Those three. Now I'm looking at it. What could go wrong in this equation?
Well, first of all, the reference state is probably not very. It's not prone to go wrong. But the two others is where there could be a problem because the alpha kind of scales the size or the significance of it of this entire term here.
Yeah, exactly. And what does that term take into account?
Temperature.
Temperature, yeah. So that's the temperature term in some way, right? That says something about the temperature relation of the U parameter in some way.
Yeah.
What does the T alpha value say something about?
Well, it says something about the shape of what the.
So if you're just looking at the equations, how correlated are alpha and T alpha in some way?
They can be fairly correlated, but
to me they look like they're doing more or less the same thing, not exactly the same thing, but they're giving you the same phenomenon in some way, right? High alpha values, low T alpha. Maybe I'm wrong. It could be that I'm wrong, or maybe the opposite way around. They look extremely correlated from this type of equation in some way.
And that was where those two are also exactly where we had this problem with things going to very, very weird values.
Yeah. So in principle, if you want to arrive at a U value, let's say you want to arrive at a U value which is 1.
Yeah.
As either you could have this value as 1 and this as 0, or this one as 0 and that one as 1, right?
Yeah.
So let's just keep this slideshow up there. And then let's have a look at your parameter table. We had that parameter table before.
Yeah, we
You
should not
showed
have
it
both.
to, I think you showed it to Bjørn, didn't you?
Yeah, that wasn't. We can't. You want this?
Yeah. So we go to the thesis now.
Okay, good.
Where is that table? Do you remember, Bjørn? Can you see in your slides what that table number was? I remember it as being something like 4 something.
In the iron
Specific parameters.
It is right here.
Oh, it's table 4.3, 5.3.
5.3. Yeah, we can use that as well.
Table 5.3, yeah. So just remember that you have kind of two terms, right? There's a right term and then there's the left term, right?
Yeah,
And then you go to 5.3 in some way.
I'm trying.
I could have spent 3 hours on this. I only have 25 minutes? Oh, that's okay.
Like this.
Yeah, going into the room. I'm going to be thrown out. Did you find it?
Oh, we need to.
Okay, so
How
let's
is
just
that not
remember
up
that
there?
equation briefly. There's kind of a left term and a right term.
But I don't know why it's not up there. Oh, this is
There it is.
weird.
Exactly, yeah. So the left term was the U ref value. That's this number here. And the right term was either this value or that value. So if I predict something, it would be like either the alpha value is big and the U ref is small, or the U ref is big and the alpha value is small. Is that what you see here?
No.
What about sodium nitrate? And
Well, one of them is significantly bigger than the other. That's
yeah,
but
but I don't know whether I see a trend, but you see this one is small, that one is big. I don't
think,
know.
well, the
when
nitrates-
it's 500, it goes down, doesn't it? It's not like 4,000 or 5,000. I don't know if there's a trend. We could probably make a trend in it. But
I think-
it's a part of the parameterization process. It's really tedious to make sure that do the parameters have a physical meaning in some way.
Yeah. I think what is observed here, this is for the solubility, the first part, the solubility, where the solubility was emphasized, and specifically for the nitrates where we have these very high solubilities. We have, and we know that the model parameters in the original parameterization gives quite significant deviations at high temperatures. And if we want to change that to give good solubility description at the high temperature, we need to scale something, and in this case it was the alpha, right?
Could you?
And that is why there is a significant difference between the value in the original work and that work, specifically for the nitrates, whereas for some of the others, the difference is much smaller.
Did you try out setting alpha to 0, for example?
But that would eliminate the entire temperature term.
Exactly. Yeah. So this means that you would have no temperature correlation, right? This is what you see in the extended uniquark model. And sometimes, if you look into the original uniquark, you will see there is a temperature correlation, but you're putting on an additional temperature correlation, which is linear with temperature. So sometimes you can actually tell yourself, okay, let's just cut away the whole temperature dependence and just rely on a built-in temperature relation in the uniquark term.
Yeah.
And the question is, could we cut away the whole alpha T alpha stuff and just rely on one U ref value, which is a kind of an interaction parameter?
No.
No. Why not? Because this is based on experience. This is based on what I would call the art of parameter fitting.
Yeah. Well. I think. I believe. Well, I know that I did some testing on this, but it was fairly small because it was very quickly evident that there needed to be some kind of temperature dependence. That was quite evident. I also think that is directly seen in Bjørn's thesis, or not in your thesis maybe, but in your thesis, in your defense presentation, I think it was.
I think it's also
That is not a possibility. So already from the start of my work, this was the temperature that was something that was included in the model and something that we worked with. But yeah, I have also seen it myself that it is needed.
You see, sorry for referring to the extended uniquark all the time, but I looked at that model so much that I know it in my head. So the fact is, if you have the uniquark model, you also have the delta UI value.
Yeah.
But that's not what's fitted. Do you know what you fit in the uniquark model?
I can't remember.
No, what you actually fit is
Or you fit each separately.
you fit each of them separately, right? And that makes a big difference, because this means that you can set all these references to something, right? This also means that the delta UI values, they're not supposed to be symmetric. These are supposed to be symmetric, but not these ones. These are completely unsymmetric. These are symmetric means that you have a table of all your parameters, just like the one you showed before, and they're supposed to have a diagonal, and the lower is equal to the top. But this is not the case for this type of parameter set. But for that type of set, it is. And you what did you do?
Well, I only defined it for the cations and the anions, right? So
Yeah.
if
You defined it for the cations and anions, but you also did another assumption. What was that?
Well, I don't know what you're referring to, but in terms of what you're saying, you could say that we do not have any value for this between cations and between anions. But
You did one simple assumption for this one, which was, I think, something like this.
yeah, exactly. Yeah,
That's what you did, right?
yeah, that's true.
And looking at a scheme like this, this was one of the things why Sanders was failing on his parameter fitting. Just remember that, right?
Yeah, that's true.
Okay. Let's see. Great. Slide 44. I'm done soon.
At some point, time runs out, right?
Yeah. You show a Kij value.
Yeah,
Is it high or low?
it's very high.
What does this mean about the model?
That for this particular instance, it's not very good.
Okay, let's do something else. Standard state data. I'm going to do this extremely quick, and I think that's one of the last few questions that I have. Maybe a general question in the end. I want to say a few words about standard state data, and hopefully you can follow me up on this. The whole first paper you wrote up, you did a very nice overview of it. I think it's great. Shows clearly what you did. One thing that I think I read in the thesis was that you were looking at Bjørn's parameters, and you were plotting everything, and then you refitted it, and then included the solubility data.
Yeah.
And I'm now stating, was it really important to refit it?
Is it really important to refit all the data?
Yeah,
That depends on the purpose, right?
depends on the purpose. Yeah.
I would say
Could you have not refitted it, used Bjørn's parameters, and refitted something else instead?
given the assumption that we can alter the standard state properties as per this, for instance,
This is a very nice example. Great that you picked that.
you can say specifically for magnesium sulfate, the difference is very small in the deviation of the solubility.
Yeah.
You have a very nice solubility description with Bjørn's parameters when we just fit the standard state properties. And in that case, no, perhaps not.
Why do you think that there's a deviation here, for example?
Why there's definition?
Why is there a deviation just there? There's two things you fit. You fit the parameters and you fit something else. What is the other thing you fit?
The standard state
The
properties.
standard state properties. Why do you have a deviation up here?
Well, in that case, the deviation there is with Bjørn's parameters, right? So in that case, we only fit the standard state properties.
Exactly, yeah. But you can also, some way you can see that the whole model performs quite well, except just here, and then at even higher modalities perform really good again.
Yeah. So,
This means that the model is correct, but the standard state data is off. In principle, when you have a model for the liquid phase, which is completely fine, you can post-fit any solubility data that you like.
yeah, but that also comes back to the point that also this all ties into essentially the correction that I made to the thesis on your request, basically, right?
Yeah.
Because the way that we compared prior to that, the way we compared there, was to state that we used known estimated standard states from the extended Unicrack as a comparison phrase. And that gives it a completely different problem and much worse descriptions, right? And that was the chosen method at the time.
I think for the purpose of understanding the whole concept, remember what I told you in the beginning? It took me 5 years to just get the first concept of it, right? Now you used 4 years.
But yeah, if you look at it post that and when you do that as here, there's clearly for magnesium sulfate not a big need to change the model parameters. But then again, if we look at systems like this and the assumption that we do not fit values that we know are true properties, then there is a purpose for it if you want to have solubility in the entire temperature range. So it's different in that way, right? If you choose from an engineering point of view to say, we just change all standard state properties the way we want, then no, we could probably get a much better representation as this as well.
So this is actually a very great slide that you picked. For example, I want to see one of the slides with an osmotic coefficient on it. Here I think it is. See, osmotic coefficient says something about the modeling the whole concentration range.
Yeah.
It says something about from 0 concentration upwards, basically. When you add solubility data, where do you improve that modeling? If you look at that left figure here,
well,
which data point will be very good?
The solubility limit.
Where is that?
Well, for certain applies, it's at this point it's probably beyond the thing that we're
The
looking at.
solubility of sodium chloride in water at 25 degrees.
It's around 7 or something like that.
Yes. So let's point at the number up there, right? So the solubility is probably somewhere just there.
Yeah.
Here. So this means that this point on the curve, when you include SLE data, will be very good. But you don't know anything about the remaining part of the curve, right? So the osmotic coefficients help you to say something about what happens before you reach solubility, right?
Exactly.
Yeah. So this is just very important to remember when you add SLE data. It gives you very much information about one point, but not something in between, right?
Exactly.
So sometimes it's a good idea to add a lot of data also for low solubility cases, if that's possible, mixing in something. So you give your range for low concentrations also. Okay. That was it. I think that was kind of the last technical point that I want to prove today. A question that I could have asked you is that what type of model do you use for the gas phase?
What type of when we do VLE, we use the entire model.
Exactly, yeah. So what do you use for the solid phase?
Well, we use what can you say about that? We use the standard state properties to find the equilibrium constant for the solids and water, basically. I don't know.
Solids are not in the water.
No. No, I don't know.
You don't know.
Well, I'm confused now.
You're confused. I brought a lot of topics today. Let's just say that you wanted to say one. You have a lot of people sitting in the room. Maybe not exactly here, but maybe mentally somewhere on a computer.
Yeah.
I want to recommend one thing to them. As a PhD student, now finalizing, you're almost done. It's 30 seconds, you're done. You're going to have a smile on your face for the next 3 months. What will you recommend to them now?
As a PhD student or about the topic?
As a PhD student.
Time goes fast, remember that. And you need to, you need to set deadlines for yourself because 3 years is a long time and it's a very long deadline in front of you, so you need to have intermediate goals. And then you also need to remember that being a PhD student is not as bad as people make it to. And you will probably be much more busy in later life.
Probably much more busy in later life.
So enjoy it. And don't get kids before you finish.
Congratulations, Anders.
Thank you.
Thank you to the examiners. That concludes this part of the formal proceedings. So what happens now is that the 3 examiners will confer about whether to recommend that the degree is awarded, and I assume that will do that in your office. Is it?
It will be.
Right, and then after which we will hear the recommendation of the committee over in the lounge where there is a reception, I believe. Can anybody confirm that?
Louisa has confirmed that to me at least.
All right, there seems to be a flag and some drinks. Okay, so thank you, and that's
Thank you.